Tunneling through the Himalayas presents immense geotechnical challenges. Risks include rock bursts, water inflows, and site uncertainty. The DRESS methodology provides to prediction drainage, excavation, and support.
All right, welcome future structural engineers to this technical explainer. Today we're going to unpack the complex physics and advanced countermeasures associated with underground excavation in the world's most active mountain range. Tunneling through the Himalayas? Well, it's widely considered the absolute pinnacle of geotechnical challenges. We're going to look at the massive forces at work, the catastrophic failures they can cause, and the advanced engineering solutions we use to overcome them. Let's dive in. Here is the roadmap for today's explainer. We'll be moving through tectonic drivers and stress fields, squeezing ground and plastic deformation, rock bursts in brittle strata, hydrogeological and geothermal hazards, advanced subsurface prediction methods, and we'll wrap up with excavation and yielding support. Lots to cover, so let's get right to it. Section 1. Tectonic drivers and stress fields. You really can't engineer a tunnel without first understanding the stress environment around it. Now, in older, more stable mountain ranges, the stress field is heavily dominated by gravity. That means the vertical stress, literally just the weight of the rock above you, is your primary engineering concern. But the Himalayas, they're a young, highly active origin, about 55 million years old. The Indian and Eurasian plates are actually still colliding right now. Because of this ongoing crustal shortening, the horizontal tectonic stress pushing in on your tunnel is way higher than the vertical gravitational stress. This creates a highly anisotropic or directionally dependent stress environment, and honestly, it completely destroys conventional support design logic. The mountain range is literally a split personality. The Himalayas aren't just one monolithic block of rock. Depending on exactly where you are, your dominant failure mode flips entirely. If you're tunneling through the Lesser Himalayas, you're dealing with weak, heavily sheared rock like phyllites and schists, stuff that just wants to deform and squeeze inward. But transition over into the higher Himalayas, and suddenly you're under more than 1,000 meters of solid rock cover. It's massive, brittle, crystalline strata like gneiss and quartzite. Down there, the primary danger isn't squeezing, it's violent, explosive rock bursts. Section 2. Squeezing ground and plastic deformation. Let's focus on that first major failure mode, the slow, relentless threat of squeezing ground in those weaker geological zones. Think about it. When we excavate a tunnel, we remove material, which inherently disturbs the natural stress field. We force the surrounding rock to take on that redistributed load. If the rock is weak, like the foliated phyllites with high mica content common in the Lesser Himalayas, a plastic zone develops. The induced tangential stress simply exceeds what the rock can actually handle, so it slowly flows or squeezes into the tunnel void over time. It's a time-dependent plastic deformation. Actually, scratch that. It's more like a relentless, unstoppable flow that can literally crush heavy steel arches if you don't manage it properly. So, how do we classify this hazard? Well, minor squeezing, under 2% convergence, is pretty easily handled. But notice what happens when convergence pushes past 5 to 10% of the tunnel diameter. We enter severe territory. At this stage, rigid supports are practically useless. They'll just snap under the immense pressure. And if you're using a tunnel boring machine, a TBM, you are in extreme danger. The machine can get entirely jammed and permanently trapped by the converging rock. The crucial takeaway here is that miscalculating plastic deformation doesn't just result in a failed grade in a structural engineering class. It causes catastrophic structural collapses. We're talking about burying massive tunnel boring equipment and entirely halting multi-million-dollar hydro projects, all because the squeezing rock mass simply overpowered the engineered support systems. Section 3. Rock bursts in brittle strata. As we deeper into the higher Himalayas, the rock gets much harder, and the danger shifts from a slow squeeze to a sudden explosion. In these deep, brittle strata, we use the competency factor to predict failure. When you have incredibly high-strength rock sitting under a massive amount of overburden, often way over 1,000 meters, the tangential stresses become astronomical. Under these conditions, the rock doesn't gracefully bend or slowly squeeze. Instead, when the stress exceeds the rock's strength, it violently ejects material into the tunnel to rapidly release all that pent-up elastic strain energy. What's really fascinating about the data we have on this is how it mathematically correlates the joint factor of the rock directly to the specific failure mode. There's a very clear threshold. You can map exactly where conditions flip from squeezing on one end to self-supporting in the middle and finally crossing that critical boundary into lethal rock bursts on the other end. That threshold represents the incredibly fine line we engineers have to walk every day. To put this into perspective with some real-world examples, the Parvati 2 headrace tunnel and the Neelam Jhelum project both experienced absolutely devastating rock bursts. During the Neelam Jhelum excavation, engineers realized that small, localized shear planes were actually acting like underground stress dams. They prevented the natural redistribution of stress, concentrating all that elastic energy until the rock literally erupted into the excavation workspace. It is an unpredictable and, sadly, incredibly fatal hazard. Section 4. Hydrogeological and geothermal hazards. Because, beyond the geomechanics of the rock itself, we also have to engineer against extreme subterranean fluids. Up there, water isn't just a nuisance, it's a structural weapon. 600. That is the staggering volume in liters per second of high-pressure water and sediment that suddenly flooded the Tapovan Vishnugad tunnel. Operating at 990 meters depth, a TBM unfortunately punctured a high-pressure fault zone. The sudden ingress didn't just flood the tunnel, it brought massive amounts of debris with it and completely halted the entire project for over 10 months. To counteract massive hydrostatic pressure like that, you have to proactively manage the water way before your excavation reaches it. We're talking drilling pre-drainage holes to relieve pressure and doing advanced grouting to create a reinforced impermeable shell around your future tunnel path. Plus, the Himalayas sit right on top of a highly active geothermal belt. We aren't just dealing with cold water. Engineers regularly hit active geothermal anomalies where rock reservoir temperatures exceed 230 degrees Celsius. You need highly specialized heavy-duty ventilation protocols just to keep the work environment survivable and stop your concrete from degrading. Section 5. Advanced subsurface prediction methods. Since surface mapping is practically useless when you're under 1,000 meters of solid rock, how do we actually know what's coming before we hit it? We definitely can't afford to dig blindly, so we use a 3-step predictive toolkit. Step 1 is tunnel seismic prediction. This bounces seismic waves to map major faults up to 100 meters ahead of the tunnel face. Step 2 is microseismic monitoring, basically listening to the microscopic fractures in the rock to track energy release and predict impending rock bursts. And finally, Step 3 is advanced probe drilling. This is where we physically drill long, small diameter holes ahead of the excavation to definitively test water pressure and verify the rock mass quality. All of this data underscores the absolutely indispensable role of the engineering geologist. They're the ones synthesizing the seismic data, the microseismic acoustics, and the borehole telemetry. Their job is to model the subsurface boundary conditions in advance. They transition the entire project from a dangerous reactive scramble into a proactive, highly controlled, mathematically modeled operation. Finally, Section 6, excavation and yielding support. Once we know exactly what's ahead, we have to select the correct mechanical approach to actually excavate these complex zones. The core debate in Himalayan tunneling is almost always NATM versus TBM. On one hand, you have the new Austrian tunneling method. It's highly adaptable, relies on real-time observational data, and uses yielding supports, which was absolutely vital for getting through the severe fault zones of the Atoll tunnel. But it's slow. On the other hand, modern tunnel boring machines are incredibly fast, but traditionally very rigid, which makes them vulnerable to jamming and squeezing ground. To survive the Himalayas today, modern multi-mode TBMs require specialized overcutting systems. They literally carve a hole slightly larger than themselves so they have a buffer and don't get crushed by converging rock. If you take one thing away for your future structural designs, let it be this: rigidity is the enemy in the Himalayas. In squeezing ground, if you build a perfectly rigid support, the mountain will simply crush it. Your supports must be designed to yield and safely accommodate plastic deformation. And, as we've seen, water has to be aggressively routed before it becomes a hydrohammer against your tunnel face. Flexibility and proactive ground treatment are quite literally your survival tools. Now, as we look to the future, things are getting really interesting. Algorithms like XGBoost and artificial neural networks are starting to predict TBM jamming risks by analyzing machine torque, thrust, and geological data in real time. They can assign a combined jamming risk score before the machine even advances an inch. So it leaves us with a provocative thought. As we tackle deeper and more treacherous alignments, will the next generation of engineers, will you, finally conquer the Himalayas not with stronger steel or bigger machines, but with smarter predictive data? Keep that in mind as you go out and design the infrastructure of tomorrow.